Hello, listeners. Welcome to Born Curious. We're so happy to be back with the first episode of Season 3. I'm Ivelisse Estrada, and Heather Min is my partner in crime. We are your co-hosts. Hi, Heather.
Hi, Ivelisse. It is good to be here with you and our listeners. For those who do not know us, Born Curious is, like its home, about unbounded curiosity. We come to you from Harvard-Radcliffe Institute, one of the world's leading centers for interdisciplinary exploration.
And as I like to say, with this podcast, we open up the doors to the intellectual candy store that is the Institute.
Today, we are delighted to welcome Merav Opher from Boston University and a past Radcliffe Fellow to speak with us about wonderful discoveries and speculations about this planet, about our solar system, and about cold clouds and interstellar medium. Welcome. We're so happy to have you here.
And I'm delighted. It's always wonderful to come back.
And we should note that Merav Opher is a professor in the Department of Astronomy at Boston University, and she was the 2021 to 2022 William Bentinck Smith Fellow at Harvard-Radcliffe Institute, where much of this work was done.
So welcome back.
Yeah, welcome back.
Thank you so much. Yeah.
And Merav, we're here today because you've just published a very exciting paper in Nature Astronomy. Tell us about this discovery that is now out in the world.
So we think that what happened 3 million years ago, the Earth and the Sun, the solar system, encounter a very massive cloud. We call this massive cloud local Linux of cold cloud. And that massive cloud is orders of magnitude more massive than what exists outside the heliosphere, our protective bubble, now in the interstellar medium. And that encounter shrank the heliosphere to sub-AU scales, so exposing Earth and all the planets to massive amounts of hydrogen, to an increased radiation, to way more dust. And there are several works that speculated that increase in hydrogen, increase in radiation could have implicated ice ages. So we're still trying to quantify. This paper at least say we encounter a very important cloud that shrank the heliosphere and exposed that to a much more extreme environment. And probably most likely there would be implications for the Earth's climate at the time.
Can you explain to our listeners what the heliosphere is?
The way I like to think about the heliosphere and talk about it to the general audience is when you look up in the sky, you see all these luminous stars, and they're beautiful. You don't realize that they're not just point sources that give all this beautiful light, but they're surrounded by cocoons. And those cocoons are very rarefied, not very dense, so it's hard to see them. But they are formed by the winds of the stars. And in that, I just have to pause to say most stars have winds. And when they have winds and they move through the mediums that surround them, they create a cocoon. Very much like if you're going a boat in a river and you have the water go around the boat. So they create this cocoon. And in our case, the sun also moves, also has a wind. And so we call that cocoon heliosphere.
And the cocoon is not really obvious to us, to the naked eye.
So it's actually the solar atmosphere. It's the outer layer of the sun called corona that, way back then, Parker discovered it's expanding and creating a wind. And that wind extends far beyond all the planets and engulf all the planets and get deflected somewhere. It's around 150 AU, and AU is our distance to the sun, so it's pretty large, and create a cocoon created by the atmosphere of the sun that also has magnetic field. So it's like a shield. I like also to think this is our home in the universe, in the galaxy. We are well within this cocoon that protects us.
And so it extends, it goes all around the planets.
All around the planets and even beyond the planets. Okay. And so it's extend, it's not as far if you think in astronomical distances. Our distance to the sun is 1 AU. This is 150 times larger. It's pretty large. And its extent, we think like it's a sphere in the direction with which we're moving to the galaxy, but might be in a different shape in the back. But that protects us from the rest of the galaxy.
What is outside of that cocoon?
The poetic way, and I think it's also accurate scientifically, that if you're taking steps and leaving the heliosphere, you are leaving your home and you are entering in the medium of the rest of the galaxy. You are in a different environment, different atmospheric environment, different temperature, different densities. So the realm that the sun dominates, the particles that it ejects, the atmosphere, cease to exist. It's end in the heliosphere. And then what you're experiencing is an environment that was created by previous generations of stars that exploded, ejected material, and from how the galaxy was formed. It's a complete different material than what we have in the heliosphere.
And this is the interstellar medium?
Exactly. So the interstellar medium, we think it's created by previous generations of stars, massive stars that explode, eject their layers into the medium, and low mass stars. It's all mixed together. And this is the interstellar medium. And it's all the environment outside the heliosphere.
When you came to Harvard Radcliffe Institute as a fellow, what were the questions that you were asking that involved the heliosphere?
One of the seedlings that I had when I came to Radcliffe was to try to figure out the fact that we have a heliosphere and the fact that other stars have the equivalent we call astrosphere, if this had any effect on life that we have on Earth. Because I knew that the heliosphere engulfed all the planets. And another characteristics of the heliosphere, that it's a shield. So it has a filtering issue. So I was thinking, well, life, was created on Earth. The fact that what I call a habitable astrosphere. We found life within this astrosphere. And my community didn't really, as any community in science, they all work separately. So I thought, would it be nice if we will find a link between people that are looking for exoplanets, other planets like us out there, or people that are looking the conditions for creating life, if it has any connection with the astrosphere, in our case, the heliosphere. So that was the title of my project, was Heliosphere, a case of a habitable astrosphere.
So that was the question you started out with,
Does
the heliosphere aid habitable planets?
Right.
But then you discovered other things.
So it started, if you don't mind, I will just delve into very quickly, how did I get to 3 million? Because when I started in Radcliffe, so I had this amazing time to just be creative and read and think about it. And I realized that the speed that we are moving, so stars move.
Yeah, let's tackle that, because I never knew that
Right.
we were just kind of headed in a direction. We're just moving.
And to give you an idea how dramatic it is, and this is actually happening in Radcliffe, because I took this speed and I converted it to something that I knew, and I was like, whoa, it's much faster than I thought. Because I think even in my community, we knew that the sun moves, so the speed is around 25 kilometers per second. And just to give an idea, what is 25 kilometers per second? The Voyager spacecraft, that is the fastest moving object that was launched, is moving a little bit slower than that. So this is 3 astronomical units a year. So our distance to the sun, every year you have 3 times that. That is a Voyager speed. The sun moves a little bit faster, 25, but it's around that. But when you convert it to other units, this is where I was like, whoa. This means that the sun moves 25 parsec per million year. And parsec in an astronomical hat is just a tiny unit outside our solar system. So most of what people been thinking, and I knew about it, is the environment of the sun within 15 parsec. But then I thought, gosh, within million years, the sun is out of that. So this is early on in the Radcliffe, I was like realizing the environment that I know outside our solar system is going to be dramatically different every million years. And this is when I started thinking where the sun was 2 million, 3 million years ago. Just also to give you a context, what we know today outside the solar system, within this 15 parsec, is this lots of bubbles. It's not homogeneous interstellar medium. It has lots of like little spherical shapes with different densities, but they are not super dense. It's warm, not very cool. It's around 8,000 Kelvin. If I think for the audience listening, you have 1,000,000 Kelvin. This is near the sun, super hot. Where stars form, we're talking 10 Kelvin. So 8,000 is lukewarm. This is the environment outside now. And the density is 0.1 particles per centimeter cube. Not very dense.
So you've got the sun, and you're saying that it's actually drifting. There's
a motion.
There's motion, and it's going in a certain direction, and it's moving kind of fast.
Right.
So where are the planets and the Earth? How is that moving? Because we've always just been taught that it revolves around the sun. So are we following the sun?
We are. So the gravity still is like the king. The gravity holds us to the sun. So the planets are rotating. And as the sun moves, think all of us are going for the ride. So the planet, the shape, the orbit stays the same. The gravity of the sun, captures us.
Do we know what accounts for the direction and the purposeful nature in which it is moving? Is there something else that is pulling it?
Look, the sun's just got places to be.
Yeah.
This is an interesting question. I'm collaborating now with Alisa's Goodman group, and I was just in her office talking about that. So she knows way more than I do. But when stars are formed, there is a distribution of speed. And I would be very interested to understand what makes that speed of the sun, the direction that we know. I think there is a statistical distribution. As the stars are being cooked in a region, they come out with a certain speed. They're never at rest. But why that and why that direction? In galaxies, you think there is something attracting, very massive. I think the sun comes from where it was first cooked that has a speed.
Because you said, there's this interstellar medium out there and it's not uniform and we're moving through it, now's when we get to the good stuff, right?
Yeah. So why 3 million years ago? Because I saw a talk before I got to Radcliffe from an astronomer, Brian Fields, and he was showing the curve of iron-60 isotopes. And iron-60 is not produced on Earth. Is produced in what we call supernova. That was very massive stars. When they die, they explode and they eject their material. And so he showed this plot that has iron-60, and right around 2 to 3 million years, there was a peak. And another peak, 7 million.
Because you're saying iron-60 was detected on Earth?
But they also, the amazing stuff that he was showing, there was like a long list of papers that it's been showing the last couple of years that these 2 peaks were detected in the snow in Antarctica on Earth, in sediments in the deep ocean, in the moon. They brought rocks from the moon and they analyzed it. Those peaks are there. So everywhere they look, these peaks seem to have been global, both on Earth, both on the moon. So something happened. And why those increased abundances in number during those years. So I knew that the explanation they were putting forward, that maybe a supernova exploded just outside the heliosphere and, showered us with more iron-60. But I heard their explanation. I thought, this is a little hard because you have to explode in the right distance. If you explode too close, you decimate life on Earth. If you explode too far, how are you going to bring it? They get trapped in dust, but I knew that dust is hard to really get, and you need right at 3 million, then needs to go away, right at 7 million. So I thought, you are really wanting the correct explosions. So I thought, maybe the sun was in a different environment. This is when I started connecting the dots, when I realized that the sun moves. So this is why I was focusing on 3 million. I just took the number of the speed, 18 to 20 kilometers per second. That means it's 18 to 20 parsec per million years, multiplied by 3. And this give you, it's around, 40 to 60 parsecs away. So I went to the literature and started reading what exists more or less in the direction of the motion of the sun that we would have crossed 60 million years ago. No, 60 parsec away, 3 million. What I was looking for is something massive, because that comes from my previous work in the heliosphere. The shape of the heliosphere depends on the pressure that comes outside. So if you have more material, more massive, it will push more. Then I thought, would be nice if we met something really massive that would have shrunk the heliosphere, exposing Earth to the interstellar medium. And then we can collect any isotopes that are there. So I was looking for any structure that was very massive. So I just looked in the literature. I'm not although I have a PhD in astronomy, but I'm not an observer. And I haven't worked in this field for, a while. I'm doing heliospheric work. But I noticed that there was this guy, Hod, in 2010, had a paper that described a large ribbon of cold clouds. It's a swap of the sky. It's pretty big.
In the interstellar medium?
It's like a necklace of cold clouds sitting there, well organized. And one of the clouds, the central one, it's called the local Leo cloud, were very analyzed by many, many other papers. And they all gave a density. So listen to that. The density is 3,000 particles per centimeter cube. And remember that the density we have outside is 0.1. Take a centimeter cube, you have not even one atom. But this says that you have 3,000. So it's 4 orders of magnitude denser. So I thought, well, that will do the trick. If we met that cloud, the heliosphere will completely collapse.
Meaning that our planet and other planets in the solar system gets exposed to the interstellar medium? Is that why we care whether it shrunk or not?
Because, so there is a piece of detail I didn't say. Iron 60 gets in dust. And when we talk about dust, it's not our dust like our home. It's like little particles, very tiny, but the heliosphere like to block these particles. So some big particles come in, but the smaller ones, the heliosphere don't come in. So if you shrink the heliosphere, then you can collect any dust you want, and that will explain a peak in iron 6. So this is what I was thinking.
We were exposed.
So this is basically like throwing the windows open in the spring and the pollen all comes in and covers everything.
Exactly.
And we perhaps were exposed to these fine particle iron 60.
If we're exposed, then it's mean that you have more dust, and then it's mean that you have, way more hydrogen atoms. And you also have something else that we didn't talk, that is radiation. So the galaxy or the interstellar medium is filled with particles. Think about hydrogen broken down, proton, with really energetic particles that are produced again from supernova. They're there. It's not a harmless environment. You have this radiation constantly. Our beautiful heliosphere shield the lower part. So if you're exposed, the lower energy is beyond GeV, come in right there. So it will affect life on Earth. All the atmosphere of Earth will be bathed in way more hydrogen. So the whole chemistry of all the layers are going to change. You also have more radiation, also going to alter. And you also have more dust that is also going to alter. So definitely what was going on Earth would have changed. The climate would have changed.
Now we're still moving, and I assume that there are more cold clouds out there.
So they're very rare. Part of, if you don't mind, I will just tell a short, funny tidbit. So when I realized that this ribbon was there, I actually called my collaborator, Avi Leib, and I said, look, I figured this out. I think this is great. I think this is what happened. And Avi was like, I think you're right. And he gave me another suggestions. And then we said, let's write a paper. Because I think we met this ribbon of cold clouds. So we put up a paper saying 3 million years ago, we met that ribbon. And then I was giving the talk in Radcliffe as my fellowship. And Catherine Zucker and Alyssa Goodman listened to it. Alyssa was here in person. And actually with Alyssa, I already told her 7 million, I think it's a local bubble. There is another structure that I thought we crossed. That is beyond what we're talking now. But one of the things that Catherine told me, so we started collaborating after she heard my talk. And Catherine said, I am working with this other astronomer, Josh Peak, and he is a world expert. I knew it because I read his papers on these very cold clouds. The main cloud of that, string of pearls was this local Leo cloud that Josh Peak had written a paper about it. So you ask me if they are rare or not. They're super rare. Most of the environment outside is warm. It's created in this explosion of massive. So it's very hot, and it's what we call an evacuated bubble. So you don't expect to see many of those. So Catherine just said, well, Josh doesn't think we crossed that. And so that seedling was like, maybe I did something wrong. Maybe I didn't calculate it right. And I go to a birthday party from Alyssa, and Josh was not there. I was eager to talk to him and say, there is something. And in the coffee break, kid you not, I got a phone call from Josh Peak. I never talked to him. He got my phone number from Catherine and Alyssa, and he called me and he said, I got sick with COVID, and I'm been calculating. I downloaded the most recent data of these cold clouds. I recalculated the speed of the sun, the speed of the clouds, and I was trying to prove you wrong because I thought, what the chance for us to meet those? And I was like holding my breath. I was like, maybe there was a mistake. And he said, but Merav, you're right. And we crossed it, and I think it's not exactly the center. It's a little bit, couple of degrees away, but we did cross its pearl. And he said, what do we do? And I even can tell you which piece we cross. And I said, don't worry, Josh. I just hang the phone, run to Catherine and Alyssa, and I hugged, and I said, it's right. This is really, we crossed that thing. Because Josh is a world expert on really analyzing that.
I do love that because he's just like, I'm going to prove her wrong. And
which is even best.
Even better because, it's ironclad.
Because he proved it himself that he was right.
Right. So then we retrieved the paper. I said to Josh, this is such beautiful. We were thinking to publish it separately, but I loved how he explained to me how he analyzed it. He took tools that I was not an expert on, because I was like, we crossed, this is big, we crossed, but I couldn't pinpoint where. So it has to have his hand really getting me the speed to tell me exactly where. And this is the name of the paper now, is the local Linux of cold clouds, because it's a tail end of that pearl towards the Linux constellation. And then we resubmitted with him, and it's finally accepted. Yeah.
So the math calculations perhaps prove that all of this happened approximately 2 to 3 million years ago.
Exactly. So the calculation that we did is completely separately to the speed of the sun, and this is what makes it so incredible, this story, because it's not even now a probability. There were other work thinking maybe these clouds are not very probable, but maybe we would encounter what we call, they didn't even think about these little clouds. They thought they call molecular clouds, some clouds that are very cold where stars form. So they thought, there is a chance in all the age of Earth that sometime we met some of these clouds. But that was a hypothesis. There were a couple of papers. It's okay, they even said every 10 to the 9 years. So not very probable. And here we are now saying, not only is probable, and we think every couple of million years we met, but I can tell you where we were, which cloud. This is what it makes it so concrete, that now we know with the highest precision, the speed of the sun, highest precision, how this string of pearls move, and we can really pinpoint in time where we met. And we get the time 2 to 3 million years ago. And hey, Iron 6 is telling us that something happened 2 to 3 million years ago. So it's all matching. And when we set to calculate what the heliosphere, so I simulated the heliosphere collapsed to a distance 0.2 astronomical unit. The Earth is at 1. So the Earth and all the other planets beyond were immersed in interstellar medium, unprotected.
So aside from Iron 60, I've heard you speak about potential impact that this may have had on the climate of this planet, as well as evidence that also coincides with this dating that people have been calculating on little underwater shells.
Yes.
So there's just more coincidental evidence pointing to something having happened at those approximate dates.
So that the other interesting thing that I also thank Radcliffe for that, because when I was doing all this work, I was trying to figure out, I knew that there would be an effect on the climate, but then I was reading all this literature, how you learn about the climate of Earth a million years ago. And they call it paleoclimate. And then I read all this incredible literature that you can figure out the temperature in the deep ocean by these sediments, these little shells called foraminifera. And as they age, they build another rooms. It's like you're expanding your home, you're building an attic and more. So you can look at the shape of the shells and figure out how old this structure is. And you can also measure, they call oxygen, O18, O16, and figure out the temperature at that time. So there are like these beautiful curves that show you what the temperature was on Earth a million years ago. It's go back to 60 million. And you can see that around 3 million and around 7 million, there was a dip. There are cooling that happened on Earth. So that was, for me, was like, wow, it seems that it's all hanging together. If you talk to people that do paleoclimate, they never think where the sun is. They are always talking about things that happen on Earth, plate tectonics, that there are streams of water that open up, that there were more volcanoes. They also include astronomy in one thing. They only include the astronomical effects with the tilt of the axis of Earth. So as the Earth rotates around the sun, the axes change. So every 10,000 years, there is more light or less light. And that is called a Milankovitch cycle. And so they include that. And they can see on the shells that the variations in temperature seem to have like a cycle that has to do with this axis. But they never asked and never thought about where the sun was. So what if the fact that we had a cooling had to do with an encounter of a cold cloud? So this is, I think, will open this paper and open a completely new area that because it's so concrete, that I think it's going to make the paleoclimatologist just start talking to the astronomers, to the space scientists. Where we were might influence how life developed on Earth. And how can we start talking about it and, thinking about the effect of how we develop. And just to finish this story, if you think about the evolution of the human species, a lot was going on around 3 million years ago. This is when the Lucy, one of the oldest strain of humanoid, went extinct. And one of the thought, both at 7 million, both at 3 million, that certain species of us as humans went extinct and others didn't because some were more adept to climate changes. So there was a whole even studies looking into it, whether the climate on Earth influenced the evolution of the Neanderthals, for the Homo species, for Lucy going extinct. And it's all happening when the sun is encountering these very extreme environments. So that for me was like, wouldn't it be amazing if that encounter also influenced? So I don't know. This is a hypothesis. But yeah.
It's the type of discovery, it sounds like, has a lot of potential. Has a lot of potential if the different disciplines can talk to each other.
Right. I think this will be the next step.
I've heard you say that your work bridges the disciplines of space science, astronomy, and climate science. Could you explain to us what the divisions are and how you're breaching them?
It's very funny because you have curiosity, like born curious, and your brain takes you to disciplines. But the way that academia and research work, you are really in silos. And this is, again, I keep saying that, but it's true. Radcliffe allow you to bridge between disciplines. People are usually on their lane, getting funded, getting the research, getting the academic careers in one lane. So space science deal with all the science that has to do within the heliosphere, the atmosphere, the solar wind, the planets. Then as you leave the heliosphere, the interstellar medium, it's astronomy. It's a different discipline. So trying to understand climate on Earth, this is not astronomy, this is not space science, this is Earth science that are doing the climate. So I think this is bringing people that are studying planets, people that are studying solar wind, people that are studying astronomy, and people that are studying climate. And even within climate, there are subdivisions who study the paleoclimate versus who is studying today's climate.
And I just want to comment on how poetic the language is of the work that you're doing.
I love poetry, so it's probably
like ribbon of cold clouds. That just sounds so poetic. It's really beautiful.
Yeah.
Helpful for the layperson to visualize.
Yeah,
I am very visual, so usually this is how I start. I have to have the story and the visual before I go with the math.
A question. So this ribbon of cold clouds, is it moving also in a particular direction or in some sort of formation?
So we don't know. This is a discussion I had with Josh several times. We don't know what form that, so we don't know how it's evolved. It's a very smooth structure. And so it seemed that they're all related to each other. Was maybe one single ribbon that broke down. It seemed a little turbulent too. We assumed in the paper that they're all moving together because it's so smooth. So they are moving, so we assumed the same speed. So we can get the speed that this structure is moving. We also assumed that 3 million years ago was not that different because it's short compared to the evolution of these clouds. But what first created it? Maybe it was an explosion of supernova that slammed into a medium and created this very compressed and dense. Yeah, they're mysterious.
We are not alone in the universe.
The mysteries of the universe will break your brain.
There's a lot of stuff out there. So can what happened 3 million years ago happen again, since we're constantly moving and everything's dynamic out there?
Absolutely. So we don't think it will happen, in the next year or the next 10,000 years. But I will imagine that because there is these cadences that we're finding, within another 3 million years ago? Yeah, probably. Those are very rare, but we live within an evacuated bubble that's called the local bubble. The size of it is 7 million. So the size of it is 100 parsec. If you account for the speed of the sun, we will be going out of that big shell in another 7 million years. So on that trajectory, we might find another ribbon of cold cloud. So I think this work and the other ones that I'm working now, both with Catherine, with Alyssa, and George Alvis with the Radcliffe wave, will set the stage that every 3 million we are going to encounter something. There is a cadency much sooner than other people thought that we are affected directly. Shrink the heliosphere, no home, we're still there. And then as soon as we leave those clouds, the heliosphere expand back, but then whooped back again. I think that's going to become a new thinking.
Yeah. And how long were we unprotected in this way? Like how
That's
long?
a super interesting question. A lot of people were asking me that. Again, depends on the size of it. So if you look at the central cloud of this ribbon of cold clouds, in one size of it is a U. So it's mean we're moving pretty fast. In a year, we are out. But we think that the other ones are very like a ribbon-like, very, very flat. Probably it's a parsec. So it's probably a fraction of a million years. So it's all my thinking that the heliosphere shrink and we are in a colder climate. There were people suggesting that even we will go in an ice age, but we will go in a very extreme climate environment for a fraction of a million years, have to survive that, and the heliosphere expand again, we're okay. So in a way of thinking, whatever life was developed on Earth, if it's us or microorganisms, whatever it is, I think it has to survive extreme changes within million years. That is a work I'm trying to pursue with my group, trying to quantify that climate. But it has its variations.
So when we go through a cold cloud again, we're saying humans, assuming assuming humans are still around, will be better prepared to survive it.
Yeah. I think it will be really neat that these several disciplines will come together and start really looking hard. What are the effects that will happen when we go through these situations, and what was the effect on Earth? Can we detect them? There are some, can we quantify and point our finger and say, this happened because we crossed a cloud? Yeah.
Really and exciting. Listening to you about what this planet could have been exposed to simply because it is part of a very dynamic galaxy,
right?
And broader beyond. I now understand why originally you came to Radcliffe to speculate on other habitable planets out there.
This would be the other next direction. Some of them are right now within cold clouds. Maybe we can even see signatures in their atmosphere of that. And some of them will leave a cold cloud, will enter, will be really neat to figure out the consequences for life on these exoplanets. Yeah.
Like maybe it sets up a more generative environment.
Right. Or more, it could be instead of something harmful, something that help life being produced. We need to still look into it. Yeah, we're starting. Yeah.
There's so much to learn and discover. Let's talk about your Radcliffe Fellowship and how you are already sort of going rogue, or rather,
rogue. I agree.
So could you talk about your year here and how it may have impacted the work that you were doing?
So yeah, the Radcliffe Fellowship was Yeah, not for many reasons. One, the fact that I'm very visual, so have a very aesthetic and beautiful building is incredible. You walk every day and as this work of art is so inspiring. But also more concretely, have this safe environment for you, as you say, go rogue. Like to think out of the box, think big ideas, not continue the same direction you've been going, and try to connect to other disciplines. And I think for me was, I have a poetic or more artistic way of doing science. So being surrounded by artists was amazing because they're also like big thinkers and trying new things and new ways of doing. So they inspire you. So just every morning, just say good morning to another person that you know is trying to think out of the box. Beside that, I did encounter, actually my office mate work on biodiversity of ants. He was Evan Economou, and the other one, Alexander Warden, was working on deep oceans, and she knew about the sediments. So I remember running after her in the corridor. So I'm reading all this about this foraminifera. Can we sit and talk? And we started meeting. She didn't know about this paleoclimate. She got super excited. So she was downloading papers. So we were meeting to go through the literature. And she pointed out, oh, this curve, I don't think it's that precise. So she was guiding me how to read it. And Evan was saying, the biodiversity is very, very sensitive to radiation. So with both of them, I started collaborations. Yeah, so it was amazing, the Radcliffe Fellowship for me. Yeah.
And you're still in touch with them? Or
Yes. Evan has now experiments with mice to try to figure out environment with and without radiation to answer this question, how life is affected by radiation. And Alexander Warden is part of my paper with Alice and Catherine on the encounter with the local bubble. So yeah, we are.
Is there a moment from your Radcliffe Fellowship that really sticks out that you think back to again and again?
As a Radcliffe Fellow, you have an option to give a private talk, a public talk, and I had chosen the public talk. So when you give the public talk, you are in a room recording. It's just you, and it's open to the public, but it's just you in that room. And so I was describing all this research, and a little anxious because it's I'm going in new realms and going a little rogue. And as I left the room, all the Radcliffe Fellows were outside waiting and clapping. And that was like, so, heartwarming to say, okay, it's okay. It's, even if you muster your bravery and you do that, have these other people that I admire that are doing amazing stuff saying, we loved it. So that was very special.
So this is fabulous. What are the unanswered questions that are driving you now?
I think what I'm trying to do in my group now is what fascinated me is that we were very precise. That even though you're thinking big ideas, you're not writing a paper that's a speculation. Because it's such a change in paradigm. So you wanted to really say, what did we encounter? I have to shout out to the Gaia instrument. There is a new satellite in astronomy, and Catherine Zucker used it before to really pinpoint the velocity of stars in an unprecedented way. So I think we are in a very, very special moment right now that we can do a precision astronomy that we couldn't do. So even if you would have thought about these questions decades ago, you couldn't have answered. And now we're ready to answer. So the next step for me is to, the most precise way, answer the climate effect. So there were papers that were written back in the 60s, what will happen if we encountered a cold massive cloud in general? And they predicted ice ages. And there was another guy in the 80s who wrote the paper, actually after that what will happen if we had like a shower of dust, and that also will create an ice age. So what I'm doing with my group is breaking down those questions. Let's just talk about the climate. And we already have a paper submitted. We are working the next, getting the state-of-the-art climate models that we have now, and drive an encounter with a cold cloud. can we predict quantitatively what will happen? That, I think, would be, again, a shift. We will be able to come with numbers to say, this is really what we think happened.
And are there competing theories about why the Ice Age happened? And what do you think when somebody comes out with a new theory?
So the Ice Age,
yeah,
that is fascinating. They actually went through the whole, I read this paper I don't know how many times because it was so neat. And they predicted water, they would be filled with water, and it would be so low in the atmosphere that would be frozen. But was 1D and didn't have the winds and didn't have all what we know today. Since I left Radcliffe, I have a postdoc, Jess Miller, working with me, and we just submitted a paper that said that the clouds be there, but not permanent. They will come and go. And we did it in a 2D model. So now I can stand on my 2 feet saying, okay, that seems that it's there, but not as dramatic. But we didn't go as low on the surface. We went in the upper, on the mesosphere. And the next thing he's doing now is looking down. So I'm okay. When they come back, I would say, I have now a 3D model with all the stuff we know about the climate. And we can even pinpoint how the winds change the temperature. So I will be able to pinpoint which physical phenomena is important and why I think the clouds will be permanent or not.
We should be clear that, we humans right now should still be doing everything we can to balance out the carbon emissions that we've been generating, because the work that you're doing, you are putting us in a broader frame in terms of, we're a planet and there's a lot of change going on.
Absolutely.
And you're looking at very long time scales. So nothing's going to, save us by giving us an ice age immediately.
Right. And if you see for example, the paleoclimate, Earth was hotter 60 million years ago and started cooling down. And there was periods with more cooling. But you can see the climate of today is climbing up like crazy. This is a climate crisis that is as dramatic as took 60 million for Earth. So you can really see why we need to be very, very active on trying to mitigate carbon emission.
Thank you. I learned so much. This is amazing. It's blowing my mind.
Thank you so much for wonderful questions. Yeah, I loved it.
Thank you so much for being here with us.
That concludes today's program.
Born Curious is brought to you by Harvard Radcliffe Institute. Our producer is Alan C. Grazioso. Jeff Hayash and Sean Hennessy are the men behind the microphone.
Anna Song, Kevin Grady, Sky Jung, and Emerson Prond provided editing and production support.
Many thanks to Jane Huber for editorial support.
And we are your co-hosts. I'm Heather Min.
And I'm Ivelisse Estrada. Our website, where you can listen to all our episodes, is radcliffe.harvard.edu/borncurious.
If you have feedback, you can email us at info@radcliffe.harvard.edu.
You can follow Harvard Radcliffe Institute on Facebook, Instagram, LinkedIn, and X. And as always, you can find Born Curious wherever you listen to podcasts.
Thanks for learning with us, and join us next time.